So we'd like to start and sort of finish an introduction to complete metric spaces. But before that, I just want to say the following about compact sets. So one of the leading applications for us has been Weierstrass's optimization theorem, which says, suppose S and Y are two metric spaces, and suppose f is a continuous function from S into Y, then if K is a compact subset in the domain, then its image set f of K is compact in the codomain, right? So you're all pretty familiar with this. You know at least one proof, so I'll not go into the proof here. Let me remind you of a leading application, which is you have two goods, good 1 and good 2, and then you have a budget set, and that budget set B is compact, right, in k-dimensional good space. And then you have a continuous utility function, real valued utility function mapping here. And so what the theorem is saying is that U of B is compact in R, right? So we know that nice budget sets like this are connected, and connectedness is also preserved under continuity, and so U of B is going to look like a closed interval, but we don't go there. We don't go discussing connectedness here. The point is that a continuous function like U will preserve this compactness of the domain, so that the image set U of B will be compact, right? So if this is compact, in R is going to be bounded. In particular, it will be bounded above. And so we'll have a least upper bound. And it will also be closed. And since the least upper bound, the supremum, is an adherent point of this set here, U of B closed implies that the sup belongs to U of B, right? So this is the max. So in particular, U max, a utility max exists, right? So we close this discussion of compactness for now. We'll come back to it a little bit when we do the theorem of the maximum. And let's briefly discuss the notion of complete metric space, okay? So in order to do that, let's define a Cauchy sequence in any metric space S. So Xn is a Cauchy sequence in a metric space S if for every epsilon greater than 0, there exists a positive integer capital N, such that for any two indices n and m greater than or equal to capital M, n, the distance between xn and xm is less than epsilon, okay? So what it's saying is that a Cauchy sequence, let me redraw that. So a Cauchy sequence has the property that as you go further and further into the sequence, the points bunch up, okay? So if I take some tolerance, some open ball like that, centered around some point, right? So let's say this is Z and I take BZ epsilon, right? So what it's saying is that there will exist some capital N in the sequence. So let's say this sequence is called Xn. So there will exist some x capital N such that if I take any 2 points, starting with capital N and beyond it, right, their distance will be within epsilon of each other. In particular, for instance, if I were to take this open ball Bz epsilon with the center at xn, so then for elements of the sequence beyond x capital N, if I take, so I'm not drawing this properly. So if I take any capital N here, for instance, any lowercase n, its distance from x capital N is going to be less than epsilon. Okay, so they bunch up very tightly. Yeah, it's there is a sort of straightforward implication here that I want to flag because I can do it using the same figure, and that is that a Cauchy sequence is bounded. Yeah. So what that means is that if I look at this sequence as a set of points, then it's bounded in the sense that I can cover all of it in an open ball with some finite radius, right? So here's how I cover all of it with some open ball with a finite radius. I start by taking some epsilon, some radius epsilon, right? And then I know that there exists some capital N such that for every pair of xn and xm beyond that capital N, they lie within epsilon of each other, right? So in particular, when I take every pair, one of them can be capital N itself. So I take x capital N as one of these points and another point, let's say x lowercase n. And since it's a Cauchy sequence, these 2 points are going to be within epsilon of each other, right? So if I were to take the center of an open ball at x capital N, drawn with the radius epsilon, right, I will be able to enclose all the points starting with x capital N, okay? So when I look at all these points, all these points are going to be at a distance less than epsilon from x capital N, okay? I'm not sure of the distance between x capital N and the preceding points. They could be outside this unit ball also. But then I use the fact that the preceding points start with x1, go to x2, x3, and after x capital N minus 1, certainly they will enter this open ball, if not earlier, right? So then I take radii from x capital N to x1, x2, x3, and so forth up to xn minus 1. Yeah, and then I consider the largest radius. The radii being considered are distance between x1 and x capital N, x2 and x capital N, and so forth, and epsilon, right? And if I take a radius even larger, then you can see that that's going to enclose all the points in xn, right? So a Cauchy sequence is bounded. So one upshot about Cauchy sequences is that instead of a Cauchy sequence, if I were to take a convergent sequence, every convergent sequence is also a Cauchy sequence. Okay, so suppose xn converges to x, then xn is Cauchy. So how do I show that? Well, take any epsilon greater than 0, right? So I know that what I need to do is I need to find capital N such that n comma m greater than or equal to capital N implies that the distance between xn and xm is less than epsilon, right? So using the triangle inequality, I know that the distance between xn and xm is less than or equal to the distance between xn and x, where x is this limit of the sequence, yeah, plus the distance between x and xm, right? But then, since xn converges to x, yeah, there exists capital N large enough such that n greater than or equal to capital N implies that the distance between xn and the limit is less than epsilon by 2, right? And so also, which is really restating the same thing, m greater than or equal to capital N implies that the distance between xm and the limit x is less than epsilon by 2, right? So nm greater than or equal to capital N implies that these two distances add up to something less than epsilon, right? And so the distance between xn and xm is less than epsilon. So a convergent sequence is Cauchy. Now, it's not true that for every metric space, whenever you take a Cauchy sequence, that is convergent, right? So the converse is not true. In particular, suppose you take a metric space which is just the set of rational numbers with this absolute value to assess distances. I can take many Cauchy sequences of rational numbers that don't converge to a rational number. For instance, suppose I was to take these successive approximations of square root of 2. It's very easy to show that this is a Cauchy sequence. Yeah, the points bunch up on each other, but they don't converge to any rational number, right? And so once again, if you were to start not from the real numbers but construct the real numbers from the rationals through some construction device like Dedekind cuts or Cauchy sequences of rationals themselves, you would basically be sort of inserting into the real line all these limits of Cauchy sequences of rationals, like square root of 2. So you would be completing the rationals in some sense to get to this real line. So the notion of a complete metric space in that sense generalizes the notion of the real line as completing the rationals. So we say that a metric space is complete if every Cauchy sequence in it converges to a point within the metric space. So if we actually construct R using Cauchy sequences of rationals, which is one of many ways to construct R from the rationals. Incidentally, one of the places which illustrates this method of completing the rationals is Kolmogorov and Fomin's 1970 real analysis book. Then R is complete by construction. Yeah. And one of the properties of R, because it's complete, is actually the Bolzano-Weierstrass theorem, that every bounded sequence in R has a convergent subsequence converging to some limit in R. Yeah. In any case, if we take R to have the quote-unquote completeness property or completeness axiom, which is that every bounded set in R has a supremum and an infimum, then we can use Bolzano-Weierstrass's theorem to quote-unquote show that R is a complete metric space. And I've done it here. I encourage you to follow the proof. Theorem 18 says that a sequence xn is a Cauchy sequence in Rk with some dp metric if and only if all its coordinate sequences are Cauchy sequences in R with the absolute difference metric, right? So this sort of mirrors the theorem which says that xn, a sequence of vectors xn in Rk, converges to a vector x in Rk if and only if the coordinate sequences converge to the coordinates of x, right? So it's a mirror image of that. And you can construct the proof as a mirror image as well. So now I want to discuss sequences of functions and a couple of definitions for convergence of sequences of functions, right? So when we move to functions, there are multiple ways in which functions can converge. And the first way is pointwise convergence, which is defined here. So it says a sequence of real valued functions fn defined on some domain U converges pointwise to a function f if for every x in the domain U the sequence of real numbers fn of x converges to the real number f of x. All right. So why do we have various definitions of convergence? So one reason is this. So suppose I take a set U and a function fn, that maps every x in U to some real number fn of x, right? So now if I take lots of these functions, they will map x to different points, right? So let me call this a sequence of functions fn, right? Then we get all these points here. All of them are images of x under different fn's, right? So I have a sequence of numbers here, fn of x, right? So we'll say that a sequence of real valued functions fn converges pointwise to a function f if for every point x in the domain, the sequence of real numbers fn of x converges to f of x, right? So let's say that's my f of x. So if I can do this for every one of these x's, I'll say that the sequence of functions fn has converged to a function f. And we did an example earlier that shows that it's not the case that, so it is not necessarily true that if the sequence of functions are all continuous and fn converges to f pointwise, then f is continuous. So in putting it differently, we could say that pointwise convergence to a function need not preserve the continuity of these fn functions, right? And the example we saw was fn of x defined to be equal to x raised to the n, and the domain being 0 to 1. And we saw that the functions converged pointwise to a discontinuous function, a function which was and the convergence was to a function which equals 0 between 0 and 1, where 1 is not included, and equaled 1 at 1, right? So the convergence was to this. The pointwise convergence was to this discontinuous function. So we've said that when we talk of function spaces as metric spaces or as vector spaces, we're going to measure distance between functions using the sup metric and the sup norm, right? So we've called that d infinity, right? So we've said that we'll measure the distance between two functions f and g using the d infinity norm, which we'll define to be the sup of the absolute differences between f of x and g of x, where we let x vary through the domain U. We saw that this was indeed a metric, right? So theorem 19 says that suppose fn is a sequence of real valued continuous functions on U, and suppose the fn's converge to f in the sup norm. This is called uniform convergence. Yeah? So they converge not just pointwise, they converge in the sup norm. Then this limiting function f is indeed continuous on U. So here is the proof. I take any epsilon greater than 0 and I take a sequence of points xk in the domain that converge to a point x bar in the domain, right? And in order to establish continuity, we must show that f of xk converges to f of x bar, right? So that will show that f is continuous at x bar. And if this is true in general, then f is continuous over the domain, if it's true for every x bar. So take any epsilon greater than 0, and in order to show this, we must show that if we take an epsilon ball, which here is an epsilon interval, around f of x bar, then beyond a certain point, beyond a certain capital N or capital K or what have you, the f of x k's come in and all lie in this open ball or open interval, right? So once k is large enough, all the f of x k's lie here. That will show that f is continuous. Putting it differently, I want to show that once k is large enough, the distance between f of xk and f of x bar, this distance, is less than or equal to, is strictly less than epsilon. Okay? So notice that f of xk minus f of x bar is equal in absolute value to, or is really equal to, f of xk minus f capital N xk, where f capital N is some member of the sequence of functions fn that we'll define as we go along. Yeah. Plus, then I cancel out this f of capital N xk, and I introduce, let's say, f of capital N x bar. So minus that, and then plus I cancel out the fn x bar, and I subtract my f of x bar. Right? So these are identical, these two. And then I consider this to be constituted by these 3 points, and I use the triangle inequality to establish that this is less than or equal to exactly the sum of these. Okay? So now I come to this f capital N function. What is this f capital N function, right? So notice first that if I take any x in the domain, right, and I've been given that the fn's converge to f in the sup norm, right? So the sup of fn of x minus f of x goes to 0. So therefore, if I take any x, I will get that the difference fn of x minus f of x can be made less than epsilon by 3. So choose one of the x's to be an xk, right? So what is being said is, because of the convergence of fn to f in the sup norm, there is a capital N large enough such that f capital N at xk minus f of xk is less than epsilon by 3. Take another x. Take the x to be x bar, right? If capital N is large enough, then in fact it's also going to be true that this difference between these is less than epsilon by 3. Yeah. And finally, for any such f capital N function that I choose, since that function is continuous, if xk is close enough to x bar, this difference fn of xk minus fn of x bar is less than epsilon by 3. Yeah. So I've shown that f of xk minus f of x bar is less than epsilon by 3 plus epsilon by 3 plus epsilon by 3. So it's less than epsilon, provided k is large enough. And so f of xk converges to f of x bar and f is continuous. So we close this introduction by showing that one of the metric spaces that we'll be working with in dynamic programming, which is the set of all functions, real valued functions with domain U that are bounded, along with the sup norm and sup metric, that this metric space is complete. Right? So the metric space BU D infinity is complete for any domain U of functions, of real valued functions. Yeah. So recall that when I say a function belongs to this space, I'm saying first that it's a real valued function with domain U and that it's bounded. So f of x in absolute value is less than k for all x, right? So where capital K is some large enough real number. What would it mean for this metric space to be complete? Let Fn be a Cauchy sequence of functions in this metric space. Right? So what we want to show is that then this Cauchy sequence, since it's a Cauchy sequence, then Fn converges to some function in BU in the sup norm. Okay. So we'll construct this function. So since each of these functions fn is real valued, as we argued earlier, if we fix, so suppose this is my domain U and each fn is real valued, it's going to map to the real line, right? So if I fix an x here and I take all these, I take this entire sequence of functions, I get a sequence of points fn of x, right? So now so what does it mean to say that fn is a Cauchy sequence? So fn Cauchy. So for all epsilon greater than 0, there exists capital N such that n comma m greater than or equal to capital N implies that the distance which I'm going to measure using the soup norm, the distance between Fn and Fm is less than epsilon, right? But what is this distance? It's the soup of Fnx minus Fmx as I vary x across u, right? So if it's Cauchy, this is going to be less than epsilon. Yeah, and therefore Fn of x minus Fm of x in absolute terms is going to be less than epsilon for all x, right? That's why it holds for this. If it holds for the soup, then this will be true, right? So now, what will this mean? So that will mean that for all x, Fn of x is a Cauchy sequence of real numbers. Right? So since Fn is Cauchy, for every x we have that Fn of x is a Cauchy sequence of real numbers. Right? Now, since they're real numbers and you have a Cauchy sequence, by the completeness of R, this Cauchy sequence converges to some real number, some number in R. And I'm going to call that number f of x. So lo and behold, if I do this for every x, I have constructed through these limits, Cauchy limits f of x, I have constructed this function f of x, right? I've constructed this using pointwise convergence. So the first thing to note is that this function itself is bounded, right? And I'll let you follow the proof that it's bounded. It's simple enough. Once you prove that it's bounded, what we need to prove is that the Fn's converge to this not just pointwise, that we have done by construction, right? But the Fn's converge to this in the soup norm. Okay? So here's how we will do that. Take any epsilon greater than 0. Right? So because Fn is Cauchy, there exists a capital N such that if I take this pair of points, some n greater than or equal to capital N and capital N itself, then the distance between these two, d infinity Fn and f capital N, is less than epsilon by 2. Okay, this follows from Cauchiness, that these points bunch up. Therefore, of course, it's also true that for every x, the difference Fn of x minus f capital N of x is strictly less than epsilon by 2, because they're all less than or equal to this soup. Okay. Next, notice that Fn of x converges to f of x by construction. So Fn of x minus f capital N of x converges to f of x minus that. And then if I take absolute values, nothing will have changed. You can regard this also as just taking a continuous mapping using absolute values. So Fn of x minus f capital N of x in absolute values converges to f of x minus f capital N of x. That's happening here, right? So we have that Fn of x minus f capital N of x is always, once capital N is chosen to be large enough, this is always strictly less than epsilon by 2, and also that this converges to this. And so by implication, this itself is less than or equal to epsilon by 2. Okay, this is true for all x. And therefore, the supremum over these, which is the distance between f and f capital N, must be less than or equal to epsilon by 2. Right? So now, if we take the sup distance between f and fn for any n greater than or equal to capital N, by the triangle inequality, this is less than or equal to the distance between f and f capital N plus distance between f capital N and fn. And both have been shown to be, so this is less than epsilon by 2, this is less than or equal to epsilon by 2. So the whole thing is less than epsilon. Right? So in other words, fn converges to f in the sup norm. So what we've shown is that if fn is Cauchy, then there exists f in the bounded function such that fn converges to f in the sup norm. So Bu with the sup norm or the sup metric is a complete metric space.